Recording. Now, ready? Yes. Everyone's ready? Action now. Now, I'm just going to record a session in case if you just want to review that later. I'm just going to post all the thing on the Google Classroom that we have. Okay, but before we start, today we have a very interesting concepts to work through, and especially the case scenario that we have is very interesting. Some of you come from the pharmacy school. Look at the champion at the back. This comes from the pharmaceutical background. And the case study that we are just going to do today, which we're just going to use principal component analysis, is for the data sets that you have thousands of chemical compounds, which you can see that there is a very cool connections between today's class, which is a math, and the one which we have this coming Wednesday, which is on chemistry for drug design. You see that you have thousands of the chemical compounds, the structures. Then you have, let's say, the features for those chemical compounds, like, for example, the bound length, the functional groups, the geometry that they have, the angles between different bonds. Then you see that we have almost 54 features for these molecules. Then we just want to just come to get some kind of an insight from that data sets. And all the things that we're going to do at the end, which is going to be through that workshop, which I'm just going to share the screen on the Python, which we have done. You see some very cool visualization, and everything is built on this topic that we're just going to cover today, which is going to be for principal component analysis. These concepts that we discussed, the math, the simple math behind it, you're going to see that how practical and relevant is that when you just come to the field of the research. For example, in a vector space that it has lots of features. For example, you have many descriptors that describe a molecule. You see that it's very relevant there. Now, before we jump straight into the principal component analysis, the ingredient from that, we talked about that last week. Everyone was so crazy, so happy that you learned one concept on, let's say, one concept on eigenvectors and eigenvalues. You saw that when you have a vector, when you have a matrix, that it represents maybe observations and its features. Then you can come to define two very important things. Eigenvectors, it was the vectors that, as we discussed last week, they were the vectors that if you transform them, you can expand or contract them, but you preserve their direction. Now, we talked about it last week, and we solved one problem with respect to that. And now we are just going to use that for this purpose because we need the concepts of the eigenvectors and eigenvalues. However, I mean, before we just start doing that, it doesn't hurt to do some practice with those kind of concepts. Now, I'm just going to stop the sharing from this the PowerPoint's content that I have prepared. We are just going to solve one quick example of the matrix, which I'm just going to also put on the whiteboard over there. Then you are just going to solve it based on the things that we learned last week, to find one eigenvectors and one eigenvalue for that. Then we continue with the principal component analysis. But also, as a bonus point, we are just going to also talk today about spectral clustering, which is also, you see that the eigenvectors and eigenvalues becomes a very dominant ingredient that you need to learn. Then as a result, I'm just going to stop the share from this slide, do the share for okay, what you see you see a white screen, huh? That's exactly what we want to do. Now, what we do is that I'm just gonna, as a kind of a very quick survey that we did. I hope that everyone is taking notes because that's the thing that you have to submit by the end of the day. We are just gonna start, before we go for the break, to start with a kind of a review. We just start with a matrix, which we have the components there. We have 4, 1, and we have number 2 And we have number 3 over there. Yes, please. Good morning.
Just left my charger over there.
You left your charger over there.
Yeah.
And what do you want to do with it?
I want to take.
Please go over there. I thought you just want to join the physics math class.
No.
Okay. Now, you got it?
Yes.
Awesome.
Thank you.
No worries at all. Now that's what we have this matrix right now in order to find the eigenvalues. First of all, you remember we just came with this conclusion that in order to find the eigenvalues and eigenvectors, we have to construct a characteristics equation. And the characteristic equation was that we said that if we have the matrix A, which is given there, I'm going to multiply that to X, what you call that, it can represent the eigenvector. Then this transformation, it comes to what? It comes to a positive number, which is either between 0 to 1 or greater than 1 at the same eigenvectors X. Then we said that this is a very important equation. If you are in the health sciences, if you're in the physics, you saw that you can just find, for example, the observable values of the Hamiltonian, let's say, energy operators on the wave equation. But you see that it has a tremendous application. Now, this one, it becomes the eigenvector and eigenvalues starting equation that we see. You see that we have the matrix A, which we have it here. It is transformed by a matrix multiplication X. But the input is what? You see that you get the same matrix into a number. Guys, look who is here. Good morning, brother. How are you? Yeah, please take a seat. You are so prepared for today. I can see you have 2 laptops with yourself. Now, what we have here. Now, okay. Now what we want to do, you remember from last week what we discussed? I'm going to do some algebraic manipulation. I'm going to take the right side to the left. Then what do I get? I get the matrix A times its eigenvector minus the eigenvalue times the matrix itself becomes how much? Becomes 0, exactly. Now, you see that from elementary school, maybe from the kindergarten, that you remember when you have one common factor in this expression, you factor it out. Then you say, oh, I'm going to factor x. Then if I factor x, what do I get from the first term? The matrix A minus lambda should equal to what? Should equal to 0. Then the problem here, you saw that the problem that we get from last week is that X is a matrix, A is a matrix, lambda is a number, scalar number. Then you are subtracting a matrix from a number, which it seems that, for example, you are extracting, you are subtracting a car from a building. What do you get at the end? Preposterous. Then as a result, in order to resolve the issue, I came here to say that we have to introduce an identity matrix, which is a square matrix. All elements everywhere is 0, except the elements on the main diagonal, which is 1. Then in that case, we saw that it becomes a characteristic equation. And now that we have everything with the same identity. Now, what was the first thing that we needed to do? Look at this equation that I have over there. It becomes our key starting point for anything that we're going to do today. This equation becomes the starting point for, first, the principal components that we're just going to find from an expression matrix. And also in the spectral clustering that you see that, for example, we're going to cluster the gene expressions for a cancerous tumors. Then this equation, it is a governing thing behind everything. Now, then as a result, what I need to do is this. I find 2 things. First of all, you see that the matrix A is given. The matrix A is given. I have it over there. But and also the matrix I, the identity, is a very popular matrix because the rank is equal to the rank of the matrix. For example, the matrix A, which I have over there, the rank is 2 by 2 because I have two rows, two columns. This is a 2 by 2 matrix. Then as a result, the matrix identity I also is a 2 by 2 matrix because these two should just match in terms of the dimensions that they have. Then the only things which I do not have here is matrices X and the eigenvector gamma, sorry, lambda. Then now, the first thing which I have to find is this. I'm gonna first find lambda. It is gonna be my first thing which I need to find. I find lambda first, then I go to find eigenvector, which is gonna be the X. In order to find the lambda, I say, in order to find, we talked about something. Let's say last week, and you remember it from the elementary school. You remember that if A times B equals to 0, A and B, there are two expressions, can be two functions, two expressions, anything. You remember that we have two options. Either A should be equal to 0 or B should be equal to 0. Let me put just or over there. We had that thing before. Now, you see we have the same thing. Two expressions are multiplied together, they become 0. It means either matrix X is a 0 matrix, which is preposterous. We cannot accept that because we say that the X is an eigenvector and we have to find the eigenvector, but we are deducing here that X is a 0 matrix. It means that X doesn't exist. Not doesn't exist. It means that it's a vector which is just 0 everywhere, which is preposterous. We do not need that. Then as a result, we said that we do not accept this conclusion, but we know that or, there is an or exists, that A minus lambda I should become 0. And we also modify that a little bit because of the simplicity for the algebraic manipulation. We remember we said that we conclude the determinant of A minus lambda I should equal to 0. That's what we did, I should say, last week. Now, in order to construct this, look what do I need to do? We have to find determinants of A minus lambda I. You have to find this one. Then if you are going to find this, we have to expand this. What is the matrix A? Exactly. I have 4 and 1 comprising the first row, and I have 2 and 3. They are the elements that they comprises the second row. This is my matrix A. I know that it comes with minus, but I have also lambda over there. Lambda, how much is a lambda? We have no idea because that's the eigenvectors that we need to find it in order to construct the principal components. Now, then I'm just going to write lambda here, and I know I have no idea how much is that. But I have I, the unit matrix. Absolutely, thank you. I know that the ranking of this matrix should equal the A, which is 2 by 2. All elements everywhere has to be 0, except the ones that it comes on the main diagonal. Means I have 1, 1, 0 here, 0 here. If it comes on the midterm, I'm just always going to give you a 2 by 2 matrices, not 3 by 3. Then it makes it so easier for you to find it. Then I know it has to become to 0. But the key is that 0 is not a number. Okay? Then it becomes, now hold on a second. Let me finish this one, then I just go to explain further. Then if I do this, what is the end result? I know 4. If you have lambda times this matrix, lambda is going to distribute itself to all elements inside the unit matrix. Then you have lambda 0, 0, lambda. You subtract then 2 by 2 matrices, then there is a compatibility for subtraction. then each element is going to be subtracted by a corresponding element. If I have 4 here, it has to be subtracted to what? Lambda, because 4 minus lambda, I have 4 minus lambda. I have 1 minus 0, becomes 1. 2, look at that, 2 minus lambda times 0. Lambda impacts 0 first, becomes lambda times 0 becomes 0. Then you have 2 minus 0, 2. Then you have 3 minus lambda, because lambda first multiplies to 1 here. Then you have 3 minus lambda. Then you have this matrix over there. So far, so good, everyone. You're enjoying the weather?
Yes.
It's gonna rain. Now, I have this matrix now. What is next? The next is that, look at the one which I have there. I need to find the determinants of that matrix. I had to find the determinants of that matrix. Now, let me come over there to show you as a side note how to find a determinant of a matrix. Look at that. I have a matrix. I'm going to call it, it's a side note. I'm just going to write here because we need it. I'm going to come with a very arbitrary matrix. I'm going to call that K. K is a 2 by 2 matrix, comes with the elements A, B, C, and D. We said arbitrary matrix. The elements can be A, B, C, D. Then we say the determinant of matrix K becomes what? Becomes, if you remember, we said it becomes the main diagonal AD Guys, I got a message on my system that I have some low resources. I have to close some application. Give me 1 second. I have lots of things open on my laptop. Let me close them. Okay, should be fine now. Okay, then then becomes AD minus BC. That's what we learned last week. The determinant of the square matrix 2 by 2. Then look at this one. What I have here is that I need to find what? I need to find, let me find a cool color. The determinant of this matrix, which I got it over here. You see? I need to find the determinants of 4 minus lambda, 1, 2, and also 3 minus lambda. And when I find the determinants, it has to be equal to 0. This is why everything comes from this equation, which we call that characteristic equation. Now, if I want to find the determinants based on the equation which we have above, how it happens? It becomes 4 minus lambda times 3 minus lambda. Look at this, it is AD, the product of the main diagonal, minus BC. Minus 1 times 2 becomes 0. So beautiful. I'm in the weather. Now, awesome. Now, what is going to left for me to do here from what we did last week is that I'm just going to over there say, I'm just going to, because look at that. The key thing is what? The key thing is that to find the value of the lambda in this quadratic equation. Then the first and immediate thing that we need to do is that I'm going to expand these two expressions, which is multiplied. If you expand it, I'm going to write it here. Not enough space. You are going to multiply 4 times all elements there, the second expression. 4 times 3 becomes how much? 12. 4 times minus lambda, minus 4 lambda. Now I come to the minus lambda, so the second term of the first expression. Minus lambda times 3. Minus 3 lambda. Minus lambda times minus lambda. Plus lambda squared. Thank you. Minus 2, which is already there, becomes 0. And I am now so close to the final expression that I need for this expression. Now, I'm going to simplify that further. I'm going to find the similar terms, simplify them. I have lambda squared, a theta. How have you been, brother? Good? Yes? Lambda squared. I'm just going to write what? Lambda squared. I have minus 3 lambda, minus 4 lambda, becomes how much, Kajal? Minus 7 lambda. And I have, look at that, 12 minus 2. 10. Awesome, thank you. Plus 10 equals to 0. Now, look at this, what we have. Apparently, I have to change the paper. I'm going to go to the next slide, and I'm just going to start from here. Equation was lambda 2 minus 7 lambda plus 10 equals to 0. Am I right? We ended up there, and we have two options to solve it, because we have to find for lambda first as an eigenvalue. First of all, you may decompose these two expressions to lambda minus 2 and lambda minus 5, that they're multiplied. If you cannot find these two numbers from high school, I'm just going to come to write this expression. You remember we said that for the quadratic equation, zero, we come to find x as these values, minus b plus or minus b squared minus 4ac divided by 2a. This is the thing which you remember from high school. And now this is the quadratic equation. I'm just going to do the same thing in order to solve it. Now, then as a result, what do I have? Now, it becomes lambda equals to minus b, minus, my b is minus 7. Then I have minus 7 becomes plus 7, plus or minus square root of b squared. 7 times 7, 49, minus 4 times, how much is a? 1. How much is c? 10. 4 times 10 becomes how much? 40. 4 times 10 becomes 40. Divided by 2a. How much is a? A. 1. 2 times 1? 2. Now, you see, we have here lambda then equals, I'm going to simplify that. You see, very surprisingly, it's very easy one. 49 minus 40 becomes how much? 9. Square root of 9 becomes how much? 3. Then becomes so easy. Plus 7 plus or minus 3 divided by 2. Then we have two options. Lambda 1, 7 plus 3, 10, 5. The other lambda 2? That's right. Plus 7 minus 3, 4 divided by 2, 2. Thank you. Then now, you see that we got two eigenvalues. For the matrix A, we started. Okay? We got two eigenvalues for the first matrix. that we started. Now, then what we need to do for the last step, then we just take the break, is that we have to find a corresponding eigenvector. The corresponding eigenvector for this equation. Now, how to find the eigenvectors? Remember on the previous page that we had. Oh, this is too nasty here. So many things written. Look at this. Oh, there are too many things written there. Okay, look at the one which is, let me take this one here. For the eigenvalue, for the eigenvector, remember this equation. We said what? We said we started with this. We said the matrix A times its eigenvector should equal corresponding eigenvalue times its eigenvector. Remember that? Then if we simplify that further, we said that if we get x times, let's say, A minus lambda I should equal to what? 0. 0 matrix. Look at that. I took everything to the other side. It becomes a 0 matrix. Right. Now, for the final thing that we do today, before we go for the break, I'm looking for what here? At this stage, I'm looking for the eigenvector. Okay? Something that you do any transformations on it, it remains the same, keeps the same direction. Now, I have the A matrix, right? What was the A matrix? 4, 1, 2, and 3. Minus lambda, the eigenvalue which we got over there. I can choose lambda 1, which is 5. But you could choose 2, I'm just going to choose 5. Minus 5 times I. How much is I? That's right, becomes 5 times 1, 0, 1, 1, 0 here, 0 here. Now, what is the end result of it? Becomes 4 minus 5 minus 1. 1 minus 0 becomes 1. 2 minus 0 becomes 2. 2 minus 5 minus 3. Look at that. This one which I got over there, it's actually what I have here. Now, what does it mean? I'm just going to write it here. I have minus 1. I have plus 1. I have plus 2. And I have minus 3. This is the matrix which is the result of this operation, which is here, right? Now, what I'm going to do is this. I know that this is a 2 by 2 matrix. Then the x that I'm looking for are also, this is a matrix. Because they are going to be multiplied together, I know that it comes to be compatible. It has to be compatible with that, right? Then if this is 2 by 2, right? Then I can build a matrix which is going to be here. I do not know its shape, but I know that it has to be compatible. That's right. Then if this is 2 by 1, you see that these 2 and 2 are compatible, which the end result is going to be a 2 by 1 matrix. Remember the last session when we talked, when you multiply 2 matrices, there has to be a compatibility. How compatible? We said that the number of the columns of the first matrix should match the number of the rows of the second matrix. You see these 2 match? 2 and 2. Then we said the resulting matrix come with what? What is left here 2 by 1 exactly. Now, what I have here, I know that the result is a zero matrix. Zero matrix means that all the elements is zero. The matrix for the eigenvectors, which I wrote it here, 2 by 1, I'm just going to call the elements x1 and x2. Now, this structures, this system is going to produce the eigenvectors if I can find x1 and x2. In order to find it, you're asking, oh my God, where is the break? We passed that minute for the break. I'm going to be done in 1 minute, then we go for the break. Now, in order to find this, I'm going to solve these sets of equation. I'm going to write it here. There is no space. I know that this value corresponds first row to the first column gives me the first element. Then it means minus x1 plus 1 times x2 plus x2 gives me 0. Then the second row to the column gives me the second 0. Means that plus 2 times x1 minus 3 times x2 should give me also 0. Let me see. The matrix was over there 4 and 1, 2 and 3. Then I subtracted minus 1, 1. Guys, so I just made a mistake here. Look at that. In the calculations which I had over there, look at that 3 here. It should be minus 5 times 1. 5 times 1 becomes 5. Then the 3 minus 5 becomes minus 2. It becomes minus 2. Then as a result, I should have here minus 2. Then here, I should have minus 2. Then you see, these equations are all similar, which means that x1 should be equal to x2. Then the eigenvectors which I'm looking for here, which is x1 and x2, they are similar. For example, we can come with an x as an eigenvector corresponding to eigenvalue of 5 becomes any number. You can write 1 and 1 times n. N can be any natural number. Becomes a vector 1, 1, 2, 2, anything that becomes the same components have, it becomes the eigenvector of the eigenvalue corresponding to 5. Oh, guys, I'm so happy. You have a very nice day. We finished our example, and the time is for what now? Any questions so far? Everyone took note of what we did?
Yes.
Okay, let me stop. Let me start recording. I just started recording. Now, when we just reviewed some concepts from the previous week of the eigenvalues and eigenvectors. Can I hear my back? Hello. Now we just move on to the main thing that we were supposed to start the day with, which is going to be the applications of eigenvalues and eigenvectors into the principal component analysis, which is going to be very irrelevant thing for this course, specifically for the other course that you have with me, which is organic chemistry for drug design. We're going to use that extensively there when we're just going to put a high dimensional chemical space into a very structured which captures the highest variations of the data that you have. However, before we jump into the principal component analysis, which I keep talking about that from last week, we have to again stop a little bit now to introduce 2 other ingredients for that, which we are just going to either, it becomes a review for some of you, but for some of you, it becomes a new concept. Then we finish on these kind of stuff before we just go for our next break. On the next session, when we come back after the break, we're just going to talk about eventually about the principle of component analysis. Now, we need to find another concept, which is going to be the covariation. Okay. Now, we're going to talk about the covariation. Then from there, we jump into the PCA method. Now, because you're going to see that by the next, I should say, by the next, after the break, you're going to see that when we construct, for example, I give you a matrix of the futures. Now, the next step that you do is that you are just going to find the covariation matrix from that you're going to do. Then you apply the eigenvectors and eigenvalues on the covariation matrix that you have built from the matrix of the futures that you have been given to. Then as a result, you see that those eigenvalues and eigenvectors finding methods that you learn, it's just going to be applied into place. It's just going to be applied onto the covariation matrix that you're going to learn today, how to find it. Now, however, before we continue, let me give you a funny example. Imagine, guys, I'm just gonna stand in the middle of the class. Okay, everybody's listening to me now?
Yes.
I'm just gonna stand in the middle of the class. Now, for example, then one of you comes here, for example, no, I'm just gonna put aside myself now. For example, you two come here to sit in the middle of the class. Then I say that, okay, as an example, I'm gonna say, okay, when you, for example, when you close your eyes, and I'm just gonna make you just rotate around yourself, the kind of games you have played. Then I ask you to walk any directions that you want, either this way, and you can only move in one direction. For example, you're standing here, you two are here, either can move in this direction or that direction. When I open your eyes, you just start to randomly choose a direction to walk away or walk close to each other. Maybe you two, you walk just at the same direction of themselves. But the other case, one of you may walk in this direction, the other one comes in the opposite direction. Okay, and that's going to be our question. If I, for example, put you two in the middle of the class, and I just rotate you randomly, and I just stop you, and either of you and both of you just want to move, how you move with respect to each other? Do you move at the same direction, or do you move in the opposite direction? Okay, and this question becomes very important. How variables, for example, if I call you both of the variables, how variables in statistics, they change with respect to each other. And that becomes important. Does the change, we do not ask how much change with respect to each other, we ask the direction that they change with respect to each other. Do they change at the same direction, or do they change at the opposite direction? For example, imagine both of you go to get a job after this program, for example, in the healthcare industry. You both get hired by the same employer, and you both receive it starts with let's say, with an income, okay, with the hourly base, for example, and both of you start with the same hourly salary per hour that you work. But imagine now, after 6 months, for example, one of you is going to get promotion, goes up and up and up and up, gets higher income. The other one, unfortunately, for example, gets penalized. You just see that your income, they penalize you, gets lower and lower and lower. Hopefully it doesn't happen. Then you see that these changes that you are just going to see between variables, if they are just going to move at the same direction, are you both of you are getting promoted at the same time, or no, you are moving in the opposite direction? One of you, let's say, for example, gets a higher income, the other one gets the lower income. And these are the things that we are just going to address. And as you can see, the thing that we discussed, for example, the covariance and covariation, it essentially captures the same thing. Look at the terminology that is used: covariance, variance means changes with respect to a mean. And changing together, covariation, like, for example, cooperation, you operate with each other. Covariation, how you change with respect to each other. And that's the thing that we're just going to find an answer with that. Then now, if we have, for example, two variables, we are very interested to capture the essence and trends of the variation amongst these variables with respect to each other. Okay, then now in order to capture that, we are going to build a matrix. For example, if the matrix has, for example, this is in the second line over there, the matrix C represents the covariation, and one element in that matrix, for example, Cij represents the covariation between observables I and observables J. You're going to see what do I mean as I bring some examples to there. But now, in overall, before I go to the next slide, which I'm just going to put forward an example, I'm just going to highlight the importance of the concepts of the covariation. The covariation represents, you form it as a matrix, that elements by elements, it represents the variation between those two corresponding observables. You're going to see what do I mean. However, you're going to see it at the end. It doesn't show the strength of the variation. It only shows that the direction of the variation. Either they are going to increase both at the same time, or no, one is going to increase, one is going to decrease. But how much is the increase? We do not get it from the covariation between two variables. And that's a very important thing. The relevance of for example, the change, you're going to see that it comes with the correlation that we're going to talk about it next. Now, in order to find the covariation as a matrix, we are just going to use this formula that you're going to see there. Okay, we are just going to stick to this formula all the time. We said that if covariation, it becomes, for example, we call that a matrix of C, then you see you have two matrices, X and X transpose. You remember X transpose, a transpose of a matrix from last week. I'm going to, as an example, remind you of those concepts today, but we are just having this as a side note. Please take a note of it, that the covariation then is a multiplication of two matrices. The matrix X itself, the future matrix X, which you are starting with, the transpose of it, and also you divide it by 1 over n minus 1. You're going to see that n is a number of the observation. For example, for example, all of you have done biology 1 and 2 here. You made the biology 1, you talked about the amino acids, and more importantly, you talked about the peptides. You remember, you put the amino acid sequences to each other, then you create a polypeptides, then depending on the hydrophobicity and hydrophilicity, you had that peptide configured into 3 dimensions. Then you decided to just give some values of the angles between some peptides, for example, between the bound of between the amino acids. You call that Ramachandran plots. Do you remember that? Angles gamma, phi, and psi. Do you remember that from biology 1? Do you remember, for example, in this scenario, you have a protein of interest, a polypeptide, that it is a 3D configuration. You run the X-ray spectroscopy to find the angles between different backbones of the protein. 3 angles of your interest: omega, psi, and phi. Every spectroscopic measurement that we get, because of the variation which is imposed by the environment, for example, the temperature, the impact of the solubility, the scattering, those stuff, every time you measure the angle for the protein, every time you measure a different number. For example, for the angle omega, for the first experiment, you get 40 degrees. The second experiment, you get 45 degrees. The third experiment, you get 47. Then you see that each time you run the measurements of the spectroscopy of the X-ray on the protein of your interest, that you crystallize it, every time you get a different measure, okay? And now, You see that, for example, if you run the experiment to find the omega 5 times, it means that the n that you have that in the covariation matrix is 5. Then at the end, you have to take note of it. How many times did I run the experiment in order to find the angle of that protein, like omega? And this is important. How many times you run the experiment to observe the observables? You're going to see the example a little bit later. Now, let's move on with this example. This is the example, and I hope that you take some brief notes of it because it becomes a part of the workshop that you saw mid-March, end of the next week. This is the first example that we are just going to start. I have two variables. For example, I have two variables, x1 and x2. It can be possibly, for example, those angles that I discussed, omega and phi of one single polypeptides at a specific temperature. X1 and X2, they are two observables, like the angles. For the first measurement, I got the values 2 and 3 for them. The second measurements, it gave the value of 4 and 5, respectively for X1 and X2. For the third measurement, I got the values of 6 and 8, and I was relentless. I went for the fourth measurement. The fourth day, I came back to the lab, I measured them, and I got these values as 8 and 10. Then I got exhausted. I said, oh my God, I cannot take any values further. Then I stopped there and I created that measurements of those two variables. Now, then as a result, I have two variables for measurements. What I'm going to do in the first step, and what I'm going to do, and this is very natural, and all the things that we do in statistics, and you have done it. You say, oh, for one variable, for example, if that variable x1 represents, for example, omega angle in the Ramachandran of that polypeptide, I got 4 measurements during the 4 experiments, but which one is which? I got 4 different measurements. Then the best idea is to take the mean of it, to take the average, like the way that you get your GPA. Then I say, okay, for the measurements of x1, sorry, for the observable of x1, I had 4 measurements. Let's add these 4 together, divide by the number of the measurements, 4. Then I get one average value for x1. I do the same thing for x2. Then the first thing which I did after running the experiments of the measurements for my observables, I got step number 1, the mean of the measured values for each observable. Okay? Then step number 1, calculate the mean. Is it okay so far for everyone? Yes? At the back. You're okay so far? Happy, happy, happy. Okay, nice. Now, the next thing that I'm going to do, I'm going to come with a kind of a terminology. I say, I'm going to center the data sets which I had. What does it mean? Guys, remember, you took notes that the mean that we got for observable x1 was 5, for observable x2 was 6.5. Then I go to the next slide, which delineates step number 2, which it says that center the data. Look at that on the top right. Still, I have my first original observables with 4 measurements for each during the experiments on the top. Now, I just come to say that, okay, I'm going to center the data. You look upset. Why? Is it that kind of hard? See, you suddenly look upset. What happened? No worries. Please stand up. Please stand up. Take your cell phone. Let it go outside. Come here, Sonia. Come here. Nothing to. There is no reason to be worried in the life. Come here, Sonia. Come here. There is no reason to be upset for someone. Please go outside. Give him a call. That's it. What happened? No worries. I'm serious. You go outside. Give him a call. Do not think of it. Go give him a call. Oh, okay. Guys, there is no way to be upset about anything. There is no way to be upset about anything. You miss someone, you know what to do? Pick the phone, give him or give her a call. That's easy. That's always what I do. No. You feel better now? Yeah? No. Now, let's go back to this. Now, next time, I'm just going to do center the data set. Look at that. The first, I have the chart of the observables there. I'm going to create a matrix. But how to center that? I'm just going to get the mean of each observable subtracted from the original measurements. For example, look at the first column. It comes with the number 2 of the observable x1. What was the mean of the observable x1? 5. I'm going to center it. I'm going to look at this matrix there. The first one is -3. It comes from 2 minus 5 becomes -3. The second measured value for observable x1 is 4. What was the mean for the x1? 5. 4 minus 5 becomes -1. The third measurement was 6. 6 minus mean, which is 5, becomes 1. And the last measurement is 8. 8 minus 5 becomes 3. I repeat the same procedure for the second observables for each corresponding measurements, knowing that the mean was 6.5. Then I saw 3 minus 6.5 gives me minus 3.5. And I do the rest. Now, it was a step number 2, so easy peasy. Huh? Then I had my measurements, I had my observables, I got the mean for each, then I centered the matrix coming from those measurements. The original data minus the corresponding mean of that observable. So far, so good, everyone?
Yes.
Everyone's happy, happy, happy?
Yes.
Yeah? Are you happy, happy now?
Yes.
How come you were missing India? Now you're just happy. No, I'm joking. Now, next step. Step number 3 is the covariance formula. Remember the covariance formula which I had over there, and I asked you please take a note of it. Look at that. 1 over n minus 1, x transpose times x. What was the x? X is the matrix of the centered data. What was the centered matrix of centered data? The one that I produced it here. Look at that. -3 minus 1, 1, 3 minus 3.5, something like that. It represents my x. Now, I have to transpose it. What was the transpose? Remember, if this is the original matrix, x-centered, we said that the transpose, guys, look at that. Everyone please stand up. Everyone. Do some muscle stretching. Oh, that's good. Please everyone stand up. Everyone some muscle stretching. Muscle stretching. Don't be shy. Do some muscle stretching. She's checking the text. Do muscle to benefit, stretch the muscles. Now you are original yourself. Huh? And I'm just going to make a transpose of yourself. What does it mean? If you are standing vertically, you have to lie down horizontally. Then it becomes you transpose. And you transpose yourself. No, I'm kidding. You cannot lie on the ground. Yeah, please sit. Now, look at that. No, you only can continue standing. No worries. Now, look at this matrix, guys, there. You see, I have 2 persons, it seems standing, 2 columns standing. What I'm going to do, I'm going to make these columns become horizontal. Like you were standing, I'm just going to bring it down. And now look what happened in this one. In this transpose, you see now the matrix is just lie down. You see the first column, -3, -1, 1, 3, becomes the first row. -3, -1, 1, 3. The second column, what is the second column? -3.5, -1.5, 1.5, 3.5. The second column, when you transpose it, becomes the second row. You see? -3.5, -3, 1.5, 1.5, and 3.5. This is now a transpose matrix. Then the columns that you had there, the nth column becomes the nth row, as I did. Everyone's okay with that?
Yes.
No complaints? Everyone's happy, happy?
Yes.
Now, awesome. Now, look back to the formula which we had over there. The covariance was what? to multiply the transpose centered matrix into the centered matrix divided by 1 over n minus 1. Now, what I'm going to do is that I'm just going to multiply transpose matrix, which is centered, to the centered matrix itself. Now, if we do that, I do not look at that. I have this one here. Look at the step 4 formula. On the right, on the box on the right, I have the original formula for the covariation matrix. On the right, I have the end result. On the bottom, I have the review of what is xt, what is x-centered at the bottom. Look at that. You remember the multiplication of the matrices. What is the rank of the xt? It has 2 rows, 4 columns. It is 2 by 4. Am I right? Look at that. It is a matrix. 2 rows. How many columns? 4 columns. What is the xt? How many rows do I have? 4. How many columns? 2. Do these matrices, are they compatible for the matrix multiplication? You say, in order to be compatible, the row of the first column, the columns of the first matrix should match the number of the rows of the second matrix. These two closest one, the closest one, they should be exact the same. Because these two they match, huh? Both of them are 4. So that they are compatible to multiply them. If you multiply them, what is the ranking of the matrix? What are left here? 2 and 2. Then the ranking becomes 2 by 2. Am I right? Now, then you see that the C which you have there is a 2 by 2 matrix. 2 rows, 2 columns. However, look at this one. How to find the individual ones which we have there. You have done it also last week. You said that you remembered from your prior studies. I'm going to review once with you. What do I care right now? I don't care about this. I don't care about this because I have the numbers there. I care about the result. My result is a 2 by 2 matrix. It means what? It has 2 rows, 2 columns. Then you see 2 rows, 2 columns. How many elements is in there? 4. Right? 2 columns, 2 rows, 2 by 2 gives you how many elements in there? 4. 2 by 2. And you can see that 1 element should be here, 1 element should be here, 1 element here, 1 element here. Am I right? So far, so good. And if I want to stand on top of this, what is the address of this element? I'm going to call this C, for example. I'm going to call this one C, the first one. Because that's a covariance, I call it C. What is the address of that element? Is it standing on how many rows? Which row? 1. The column 1. Then the address is C1, 1. Huh? How about this one? C1, 2. How about this one? This is C2, 1. This one is C2, 2. We say the first represents the number of the row which is standing. The second represents the number of the columns. Huh? Now, I'm looking for this one as an example. How much did I get for this? This is C11, huh? It means that this is the result of multiple row number 1 of the first matrix times the column number 1 of the second matrix. 1 represents 1 here. 1 represents 1 here. The first one, the row, the second, the column. That represents that one. Look at this one. I'm just going to find the first one, then you can do the rest. Although you're not going to be tested on this one. Okay? Now, look at the first one. The element of xt-centered time xt-centered. The first element is how much? 20. But how did we get that? Look at the matrices at the bottom. The first one is row number 1 times column number 1. Row number 1, what do you see? -3, -1, 1, 3. Column number 2, column number 1, what do you see? No, column number 1 of the second matrix. I'm just going to multiply 1 by 1. -3 times -3, how much do you get? -3 times -3 plus. -1 times -1. Plus. 1 times 1. Plus. What is the last one? 3 times 3. Because what did I do? For the first element, C11, I had to multiply row number 1 times column number 1. How much do you get? -3 -3.
Plus
9. It's fair to start. Plus 9. How much do you get for this?
plus 1.
How come times 1 by 1?
2.
1 times 1. 3 times 3. 9. I have to add them all together. 9 plus 1. Hello.
Sir, I want to borrow a laptop of similar.
It depends from whom.
Similar, someone must call and. No, no one. No, there is no symbol in this class. I'm so sorry.
No worries. Okay. Guys, are you serious? You didn't want to lend your laptop? You said there is no SIMRA?
No.
You have no SIMRA?
No, sir.
Oh, okay. Now, 9 plus 1 becomes 10. Plus 1, 11. 20. You see, we got the 20 there. Huh? We got the 20 there. The first element is 20. Now, as a final thing that we do before we go for work, I'm going to do this for the second element. Look at that. C12. How much you get in the matrix? 23. Huh?
Yes.
C12, you get 23. C12 is what? Row number 1, column number 2. Row number 1 times column number 2. -3 times -3.5. -1 times -3. And you continue with the rest. And at the end, you get the number 23. But you can do it later. We do not do it now. Huh? Yes? Awesome. Now, but we got X transpose times X. We said that you have to divide it by number 1 over n minus 1. N is the number of the experiments that you do to measure the value for that observable. How many times? Look at the matrix, look at the chart which I have there. I have 4 measurements. Means that I repeat the experiments for 4 times. Which it means that then as a result, I divide the end result, the matrix which I got, by 1 over 4 minus 1. 4 minus 1 becomes 3. Then every element which I got in that matrix is multiplied by 1 over 3. Then that's going to be your final calculations for the covariance matrix. Now, in the next slide, you see that the covariance matrix is built like that. The end results, when I just multiplied the matrices divided by 1 over 3, I got it there. Now, look at this one. The very final thing which I want to say, then we finish the course. Now, before the break is that, look at that. For the covariation matrix, which I have over there, C11, remember at the beginning of the class, I said that C11 represents the variation between observable 1 and observable, I said C, let's say, I said C, I, J, the elements in the covariation matrix. You said, what is the interpretation of any numbers which I got there? What do they mean? Why did I care to find it? It means that, for example, Cij, here it's C11, C21, means it measures the covariation between element I and J, between observable I and J. For example, if we have C12 over there, it means what? Means the covariation between observable 1 and observable 2. We call them X1 and X2. It could be angle psi and phi in the polypeptides. Means that the covariation between these two observables is captured by this number. Then that number that you got has lots of information to convey. But look at this one. The covariation between C12, we have C21. C21 is a covariation between element observable 2 and 1. It was observable 1 and 2. Are they going to be different? No. The way that you two are separating with each other, for example, the way that, for example, these you two are interact are the same. Covariation between element observable 2 and 1 is the same between 1 and 2. And that's why you see the matrix that you have there. The off diagonal, you get the same number, 7.67, 7.67. Now, at the same time, look at C11, look at C22. Covariation between observable 1 and observable 1. Covariation between observable 2 and observable 2. Which you call this one the variance now, because you are measuring how you yourself are changing with respect to yourself, with respect to a mean. Then as a result, you see that the diagonal elements, they are the variance, the off diagonal, they are the covariance, that they are symmetric and the same. And by saying that, I need to ask you any question, guys, so far. Anyone is missing anyone or anywhere? No, everyone's okay? Happy, happy? Okay, now, then I'm just gonna coding up. Okay. Okay, shall we continue? Now, guys, you have also one workshop for this part of the lesson. Then it becomes eventually the very final one that you are just gonna produce as part of the workshop. Nothing further needs to be done. Brother at the back. Yeah, everything's good. Happy, happy, happy. Awesome. Glad to hear that. Then essentially this one is the very final thing that we're just going to do for today. There is only one writing things that you need to do, part of the workshop. Then you submit it today, then you leave. We just meet next time. Okay. Now we are going to talk about very briefly because we talked about, let's say, as I said, the whole thing that we plan to do for this week is to get into the concepts of the principal component analysis. We needed to do some preliminary stuff, like, for example, we had to talk about what is, let's say, eigenvectors and eigenvalues. Then we just moved to talk about the covariance matrix. We did one example on how to use pen and paper to find the covariance matrix. When we just go to talk about the principal component analysis, you're going to see that you are just going to get that PCA from finding the eigenvalues and eigenvectors of the covariance matrix from the matrix of the features that we had before. Then you see that you start with the matrix of the features. You get the covariance matrix built from it. Then you get the eigenvalues and eigenvectors. Then you work towards finding the PCA, principal components of that. Then you come to visualize it to see how it looks. That's the road plan. Then, but before we just move on there, I said that it's not a bad idea to talk about, let's say, what is the correlation, because what we talked about, let's say, the covariance. We said that the covariance, you get it, for example, you saw that we had an example. We said we run an experiment, like, for example, we have a polypeptides of the amino acids. We just put them in the physiological conditions, for example, with the pH, predetermined the temperature. We saw that the three-dimensional configurations, then we come to say, what are some characteristics angles of Ramachandran angles? You go through the measurements, like say X-ray spectroscopy. Then you saw that for each measurement, that how many times that you do, for example, between two angles, between psi and phi, you had 4 different measurements, then you build the covariance matrix from those measurements, which has been done 4 times, then you say that, for example, the covariance between psi and phi, which is symmetric with the covariance between phi and psi of that angle in that polypeptide, which are going to be the same, represents the direction of the variation. Means that are they going to both increase at the same time? For example, if there is, let's say, for example, if pathologically, if that protein is expressed at the neural tissue, or misfolding of that protein has some pathological, I should say, cognitive dysfunction. If, for example, if the misfolding of the protein causes one angle, for example, phi, changes, decreases, what is the response to the angle, let's say, psi? Will it also increase or will it decrease? And that was the answer that we can get from having the covariation between these two angles. Then if both of them are positive, if the covariance between phi and psi is positive, it means that if one increases as a result of the protein misfolding, the other one also increases. But no, if this was negative, it means that if one angle due to the misfolding of the protein, one angle decreases, you can expect the other angle decreases. They just move in the opposite direction. And that was essentially the concepts of the covariation between different variables that we discussed. But now we just find something, a concept, which is similar to the covariation, which is called correlation. And we're just going to work with that extensively because we are just going to also plot them a lot to see the correlation between the variables. Correlation, you want to say something to me? Are you upset? Are you happy? Okay, now we said that correlation is like covariance. It measures the direction of the change between two observables, but at the same time, it shows the strength of the dependency of one into the others. For example, with the correlation, for example, with the covariance, we said that if both of them are positive, for example, like the case that we had over there, look at that. We had, for example, C12, which represented the correlation between the variable 1 and the variable 2. We got it something positive. That positive number means that changes happens in the same direction with respect to the other. If one increases, the other one increases. But what is the strength of this relationship? Correlation comes to answer that question. For example, like the one that you saw before, the covariance, it could adopt any values from -infinity to the +infinity, like the one that we had before. It was 3 something. But correlation is something between 0 and 1, or between -1 and 0, which it means that the variation, the range of the correlation is very limited between 0 and 1. If the correlation between two variables is 0, it means that they do not have any dependency on each other. If the correlation is +8, let's say +0.9, it means that not only they change at the same direction, but they are so co-interrelated. They are so strongly dependent on each other. Okay, and the strength of that dependency comes with the absolute value of the correlation. You're going to see that. For example, I said that on this slide, if the correlation measure, which is noted as R, is 1, means they have perfect positive relationship. If this is -1, perfect negative relationship. If this is 0, it means that there is no relationship at all. Now, I'm just going to move on to talk about, let's say, how to find the correlation, which we call that the Pearson correlation before we just go for our next break. Look at that. With the concept of the correlation that you see over there, with the formula on the top, you see that we have X and Y. These are like, let's say what? Like variables. It can be the same angles that I discussed with the Ramachandran plots of the polypeptides. In order to find a correlation between these two variables, first, you have to find the covariance between them. That's the thing which we learned before. Then you have to find also the standard deviation between each variable at the denominator, which I call that sigma x and sigma y. We call that the standard deviation of each random variables that we discuss. You're going to see that by an example that we're going to talk about that later. All right, we talked about this one. No need to continue. Now, this formula that we have there, this is called a variation of the correlation measurements to see the relationship between two variables, x and y. Look at on the top. We're just going to put that as a number. I hope that you take notes of this formula. As we move along the next slide, you can just see how this formula, it can be used when you have some numerical numbers. Then I advise you to take a note of that one. On the next slide, you're just going to work with that. For example, with the variable x, it can be like the x1 in the previous example that we had with covariation. Or x can be, for example, the angle psi of the backbone of the polypeptides. You see that we have x hat on the top. This is the mean. Do you remember before the break, we said that, for example, with observable x1, we get the mean of it. And that's the same thing. And we have y bar. Y bar, it is also the mean value for the observable or random variable y. You have xi and yi, and you have the sum over that. It means that for each measurement, you have to subtract it from the mean, multiply that to the corresponding observables. Then at the end, you have to sum them together because you have the sum. Now, at the bottom, with the concept of the standard deviation, you have sigma x times sigma y. Okay? Look at that. I'm just going to use the whiteboard, which I have to share the screen with that to explain about that. Remember the xy, standard deviation. What you need to find out is that you subtract the value from the mean, take it to the power 2. You add them together, you take also the square root of it. It becomes the standard deviation. I'm going to talk about that on the whiteboard before we just go for the example. Now, we just go to this example. No, not kidding. No worries. See you next week then. No worries. You too. Bye. Okay, now, look at this one. This is the example that we have. Then after that, the finish this example, we just go for our next break. Okay, look at that. For example, we have a very tangible example here. We have, for example, 5 people in this class. We take the height and we take the weight in kilogram, and the height, let's say in feet. No, the height is going to be in meters then, not the feet. It becomes too small. Okay, they have these ones. Now, what we want to do here is that at this stage, it is very obviously, at this stage, you know how to find the covariance of these two random variables. One random variable here is the height, and the other random variable is the weight. We know that if you just want to find the covariance between them, how to proceed. But first of all, you may ask yourself, you have 2 random variables. One of them is weight, one of them is height. What does covariance mean with respect to these measurements? For example, I have the covariance between height and weight. What does it mean? What is the interpretation? Yes, it means that if you find the covariation, you are looking to this answer that if someone becomes taller, will it necessarily weigh more and heavier? If that's the question, then we find the covariance. If the covariance becomes something positive, it means yes, for that person, that you find the covariance and it becomes positive, it means that if that person grows taller, it should weigh heavier. But if the covariance becomes negative, it can be interpreted like that to say that, oh, it's very interesting. It means that if the person becomes taller, it should weigh less and lighter. And that's the exact opposite of the movements. The height grows up, the weight grows down. And the covariance between these two random variables as weight and height, has that interpretation. If you grow taller, will you necessarily weigh heavier or lighter? How to answer that? Using the covariance. And we know how to find the covariance. We have to find what? The mean of each observable. We find the mean of the weight. We find the mean of the height. We just find the centered matrix. How to find it? Each observation is subtracted from its corresponding mean. Then you transpose it. You product it by multiplication. Then you divide 1 over n minus 1, which we have n here as 5. That's what we did before. Then as a result, you get the 2 by 2, let's say. For example, the matrix. Why 2 by 2 matrix? Because you have two observables, x1 and x2, height and weight. Then the matrix that you get, I just write it here. Then the covariance that you get, it is like that. Remember, it represents, for example, this one. Remember, it becomes 2 by 2 because you have height and weight. For example, this one represents height. This one represents weight. This one represents height. This one represents weight. Then the number that we get here is the variance for height, variance for the weight, and these numbers that we get here, these are the covariation. For example, height and weight. The covariance between height and weight, and you remember these two numbers are the same, because they are symmetric. Of course. Now, what we did now, it was a review of what we did before. Now, what I'm going to do is that I'm just going to use this one to just go to find the correlation. Remember, the correlation formula, it starts from the covariance. At the numerator, you have the covariance, then divided by the products of the standard deviation of each. Now, look at the formula here. Now, step number 1, you remember when you go to the formula, when you look into the formula, you see that you have x bar and y bar. X and y represents your random variables. When you put the bar on top of it, it means that they are the average values of those random variables. Then if x was the height and y represents the weight, then x bar means the mean and average of the height, which you average it over the same number, which is 5. And I do the same procedures for the height and weight. Does it make sense so far? Yes, please. Now, look at this one. The next chart that you're going to see, it represents everything in the compact form. Look at that here. The first two columns is the numbers which we had from this matrix here, height and weight, 1.5 and 60. Look at that. X is 1.5 and Y is 60. Now, in the next column next to that, because I'm rebuilding this formula on the top, I did everything next to that. For example, then I had to measure the deviation xi minus x hat, x bar, sorry. Xi means observation of that random variable at the ith time. If I is 1 means the first observation. The first observation is we are at the first row. It's 1.5. 1.5 minus the average, which is 1.7. Look at that. The x bar is 1.7, which becomes minus 0.2. And I did the same thing, the next column, which is yi minus y hat. which is for the height. The y was 60 minus exactly 0.4, which is the average for the y bar. Now, what else did I had to do? Look at this formula. I had to multiply these variations together, and I did it here. Minus 0.2 times minus 12.4, I got that number. Okay? Now, at the same time, look at the denominator. When I had to find the standard deviation, means the observation minus its mean squared. And I had to also, that's right. Look at that. That's what I did. Observation. And I did, let's say, the variation, I found it. Look at that. If it was, let's say, for example, xi minus x naught, look at that. The same value there, which is minus 0.2, it is taken to the power 2 because the formula at the denominator, it uses the variance. Variance is always raises to the power 2. Then that's what I did. I did for all the observation. 1.5, 1.6, and I repeat everything like that. Now, what do I do? The next, you see, in the formula, at the numerator, everything is multiplied. Every observation which you made, when you subtract it from its mean, then you have to multiply that to the corresponding observation at that experiment. Look at that. The sigma xi minus x bar, xi minus y bar. It means that minus 0.2, everything is multiplied to the other. You see? And you get this. You get the sum of it. You get also the sum for the squared one, which we had, 0.04, 0.01. You add everything, and also for the y, and you bring it back to this equation. On the top, you had the sigma of the products, which is 6.5. At the bottom, you had to multiply these two and take the square root of it. Why? Because all comes from this definition of the correlation. Now, you see the end result, the correlation is approximate to 0.997, which we get two interpretations from that. The first thing is the sign of that number. Look at the sign is positive. It means what? It means that the direction of the variation between these two variables, that one of them is height, the other one is weight, they are at the same direction. It means what? It means that if someone grows taller, necessarily should weigh more. And that was a question that we asked ourselves initially, that why did we measure the correlation? For example, in the other workshops that we're going to have, if you find the correlation of the gene expressions with some phenotypic traits of that person, you see that the correlation, it becomes a very important parameter to convey lots of information. The second thing that we get from there is that the absolute value of the correlation. You see, this is 0.997. We said that the maximum value for the correlation is how much? 1, because there was a bound between that, between 0 and 1. And if it becomes closer to 1, it means that they are so strongly correlated. It means that this is not a random, it's not a chance that if someone goes taller, heavy, it becomes more heavier. They are heavily correlated. And that's it. And probably, let me talk about one very important thing. You're going to see that also after the midterm, we're going to talk about causation. And at this stage, I wanted to remind you that when you find, we have two different concepts. The first concept is the correlation. We just started with the covariation. We extend it to the concepts of the correlation, and we see what does it mean. It means that two things are correlated. For example, like what? For example, if it's raining out there, there is a correlation between the rain and the number of the umbrellas that Shoppers Drug Mart across the street they are going to sell. It's obvious, huh? When it gets heavier in terms of the rain, they're just going to expect to sell more umbrella. Isn't that obvious? Yes? But we have a different concept that is called causation, that something causes the existence of something else. These two are something different. It means that if correlation exists between the number of the umbrellas sold and the rain, there is no causation between them. It means that the umbrella didn't cause to have the rain. It becomes ridiculous to say that. The umbrellas, because they were sold, it caused the sky to have rain. They are not they are different. Then that's a word of caution. As we move along the course, remember, correlation and causation, they are two different concepts. You do not confound one with the other. Sounds good? Any questions? Everyone is good? Happy? Okay. Now, do you have to share your screen? Remember, in 15 minutes, somebody gives me a signal, okay? Somebody, all of you can just give me a signal. Now, the chart, which I forgot to mention before we just went for the break after the covariance and the correlation, there is a comparison between two. I'm very quickly, I'm just going to review that before we just go to the main thing, which is going to be the principal component analysis lecture. Bless you. Then what we discussed before, it is in summary discussed over here as a comparison. Remember, we discussed two things between variables of the experiment. It was the covariance and correlation. There are differences and comparisons between them. In terms of the definition, you see that the covariance measures the direction of the relationship, but we said that it doesn't measure the strength of the relationship. But correlation measures both the direction and the strength. Okay? Now, and the formula also, we saw that there between the covariance and correlation. You saw that with the correlation, it comes also from the covariance calculations, but at the end, you have to divide it by the products of the standard deviation of all the observables that you had in that experiment. We did the numerical examples there. And one thing very important was that the covariance didn't have any range of the numbers. It can extend from minus infinity to plus infinity. But with the numerical examples that we had, you saw that we had some covariance more than one. But you remember with the correlation, we said that this is bounded between -1 and +1. In terms of the units, for example, you saw that we didn't mention that over there, that with the covariance, for example, the covariance between the heights and weights becomes in terms of the units of each. For example, if the height is in meter and the weights in kilograms, the covariance adopts it of kilograms into the meters, but for the correlation, because you divide it at the end by the same unit, you get the correlation unitless. Then it becomes just a number without having any units attached to that. Now, in terms of the interpretation, you saw that with the correlation, because it both represents the direction of the dependency and its strength, it was much easier to draw the interpretation and conclusions over the correlation rather than the covariance. And the thing which I said that as a warning was that we do not do that in case of, as a kind of a word of warning, we said that correlation and causation, there are two distinct things, which we are just going to get to that later in future discussions. Now, the things that we are going to discuss, we eventually go to a kind of a surface of the PCA. By the next session, we get into more the math behind it to do the analysis itself by using the matrix of the features. But in terms of the PCA, within the next 10 minutes that we have to discuss, but we expanded more on that by the next session. We look at the PCA as a very powerful technique, both in statistical learning, in the high dimensions of the feature space, and also a very important, let's say, AI technique like the machine learning, when you just want to reduce the dimensionality to run the algorithms on that. But however, before we just go into that thing, the key concepts of the PCA that I'm just going to go through them next week. I'm just going to give you some numerical examples. Then we take every step one by one to find the direction of the highest variation. But over there, I'm just going to very briefly explain about that. Okay. Now, when it comes to finding the PCA, we have at least 4 ingredients that we had to be familiarize ourselves with. Such a hard word to pronounce. I think everybody's tired. I myself tired too. Then it's so hard to pronounce the right words. Then in order to find the PCA, you're going to see that next week, we need 4 ingredients. By now, we have the knowledge of all those 4 ones. The first thing that we need to know is that to know the concepts of the variance, which we learned about that at the same time as we're talking about the correlation. We saw that by the variance, we mean that, for example, each measurement, how far away is it from the mean of that sample? We talked about the covariance matrix today, and that was the reason that I postponed the concepts of the PCA until now, because we needed to know about the covariance, the definition of the covariance, its significance, its interpretation, and also how to construct it. By now, we know what is a covariance matrix and how we can build it and how to interpret each individual values into that in that matrix. Also, this today and last week, we talked about the eigenvectors and eigenvalues. The most important thing that here we needed to know about the eigenvectors. For example, by the next week, then we have the numerical measurements and the numerical analysis of the PCA. You see that the eigenvectors of the covariance matrix that you measure and you find, it represents the direction of the highest variations of that experiment. It means that this is the direction that they can exploit most of the information. And also the eigenvalues represents the magnitude of all those informations that is captured in that direction. The bigger the eigenvalues, you expect them to have more information attached to that direction that you're taking as a PCA in your analysis. Now, I'm going to very briefly talk about, what time is it now? Still have a couple of minutes.
4:27.
How much?
4:27.
Okay.
It's coming now.
You're counting every single second, huh? Now, the steps, which is important also. Guys, are you listening?
Yes.
Seriously?
Yes.
Are you sure?
Yes.
Positively sure? Yes. Now, the steps that we're going to do next week, this is this. We said that, okay, first of all, we have to standardize the data. This is the step number 1. It means that we have to, there are some formula with that. We talk about that later. Now, the next one is that we have to find the covariance matrix as what we did today. Today, we learned how to find the covariance. Standardization of the data, which means that you rescale it in order to have the mean of 0 and the standard deviation of 1 by using the Z statistics. We are going to talk about that next week. It's a very easy thing. The most important thing was to find the covariance matrix. Bless you, that we know how to find the covariance matrix. In terms of the eigenvalues and eigenvectors of the covariance matrix, we have done a couple of examples with the numerical values. We know how to interpret them also. And the next one is that we have to sort the eigenvalues and select the, let's say, the top principal components, maybe 2 or 3 from the eigenvectors that we have decided. And also the last step is going to be the transformation of using the selected principal values. And also, we can also visualize it. In terms of the very brief case study that I'm just going to share the screen with you, but we will work with that. By next week is the data set which it captures the information of the molecular components. For example, the bound angles, the bound length, or for example, you look at this one. It talks about the molecules that they are biodegradable. It's a brother at the back, you are pharmacist. Please come to the front and explain what is biodegradable in terms of the molecules. I got you off guard. No worries, I was joking. Take your seat. I got you completely off guard. We're going to talk about that next week. Then, for example, you're going to see that there are two types of molecules. You can, in terms of the metabolism's features that they can have. These molecules come with some features that, for example, you have either topological descriptors, or you are describing, for example, its polarity as, let's say, electronic descriptors. Next week, you are going to see that these data comes with these features. For example, the Zagreb index, which is a representation of the topological index. We work with these data sets next week when we just work in details how the PCA works. Then I'm just going to show you how to upload the data, how to read the data, how to do the basic statistics on those data, and at the end, how to do the PCA without pen and paper, using the computer, the Python, how to just find the two directions that the most information is captured there, becomes the two eigenvectors. But we do that all next week, because today we did lots of things. We are so exhausted. I'm just going to leave this off by next week that we talk about that. Now, any questions so far? No? Then remember, what we end today, oh, I'm just on time. No one is just raising hands to show me the time is up. Then what we did today, we prepared ourselves for next week that we're just going to use everything what we have learned so far about the covariation, covariance metrics, correlation, eigenvectors, eigenvalues to just do a phenomenal job on pharmaceutical data, which is there. We just use the Python next week. I'm just going to show that to you how to do. Then you can find two directions that conveys the highest level of information, because there are two orthogonal eigenvectors in that space. By saying that, I'm just going to thank all for your hard work today for the class. And now this is the